to start the class, and today we will discuss about the implementation of the filters. And in this we are going to describe the concept of the filter implementation, and we will also discuss what is the quantization effect due to the implementation of the filter. And as we know, for the purpose of the filter designing and realization, we have to follow the 4 steps. And the first step is define the filter specifications. That is, we have to decide what is the pass band, stop band, optimization criteria. And then in the step 2, we have to derive the optimal transfer function for the FIR or the IIR. And in step 3, the filter realization takes place. That is, we have to decide the block scheme, flow graph, direct form realization, lattice realization, or the here the cascade or the parallel realization. And in step 4, we have to do the filter implementation, and that can be implemented using the hardware concept or the software concept. And during the time of the implementation, accuracy issue takes place here, because in this one we have to quantize the number of the bits. So here the question is whether the implemented filter is same as the design filter. We can say no, because in this one we are presenting the filter coefficient by a limited number of the bits that depends upon the bandwidth of the processor or bandwidth of the software. Similarly, we have to also decide the number of the bits for the purpose of the signal. So we can say here the implemented filter is not same as the design filter. So in this lecture, we are going to discuss these topics. What will the finite word length effects when we are using the fixed point implementation? If we are using here the floating point implementation, naturally there will be the shortest of the error, but in the case of the fixed point, there will be a larger error. So we have to select only the fixed point implement. Here we have to select the fixed point implementation, and for that purpose we have to discuss about the coefficient quantization, overflow, and quantization in arithmetic operations, scaling to prevent overflow, quantization noise, that is the statistical modeling, and we will also discuss the limit cycle oscillations and orthogonal filters in the next lecture. Here, first of all, we will discuss the finite word length problem. So far, we have discussed that during the time of the design, whatever is the coefficient and whatever is the value of the signal, that will be considered as it is. It means we have considered the infinite precision, that we have assumed that the infinite number of the bits will be utilized in order to represent the coefficients as well as the signal. But in practice, what is happening here? In practice, number of हेलो, अभी क्लास में थोड़ी देर बाद.
Sir?
Yes.
Sir, PPT is not visible.
And it is not visible from the starting or presently?
Yes, sir. From starting, it's not. Sir, it was visible at the starting, but now from 5 minutes, it's not visible.
Okay.
Yes.
Now, what's the position? Is it visible?
Yes, sir. Yes, sir.
Okay. So again, we are coming to the first slide, and as we have discussed that the filter quantization effects has to be implemented here, and the steps during the time of the designing are the first we have to define the specification.
Sir?
Then, yeah.
Sir, PPT again, it's not visible.
Now?
No, sir. आप में से किसी को पीपीटी दिख रही है स्टूडेंट्स? अंशिका, हिमांशी, कोई बताइए.
नो मैम.
अच्छा.
तो रिपोर्ट करना चाहिए ना, नहीं दिख रही तो शांति से बैठे रहते वही. Now
Yes, sir.
it's okay.
Yes, sir. Yes, sir. It's okay.
Okay. So we are discussing the here the filter implementation in this lecture, and we know that during the time of the designing we have to follow the 4 steps. The first step is the we have to define the specification, and in the second step we have to derive the optimal transfer function for the FIR or the IIR, and in step 3 we have to use the filter realization, that is what is the filter block diagram and flow graphs and the direct form realization and the lattice realization. And step 4 is the filter implementation, that is related to the hardware implementation or the software implementation. And naturally in the time of the implementation accuracy issues takes place, because in this one what is happening, we are using the limited number of the bits in place of the infinite number of the bits here for the presentation of the coefficients as well as for the presentation of the signals. So now the question arises whether the implemented filter is same as the design filter or not. Naturally, it is not same as the design filter, because in the design filter we have assumed the infinite precision, but in the case of the implementation, now we have to select a finite number of the bits for the purpose of the representation of the coefficients as well as for the purpose of the representation of the signals. So here, so far we have assumed all variables will be represented by the infinite precision, but presently we are moving to the finite precision here. So due to these practices, what will happen? The issues will be related to the quantization of the filter coefficients and the quantization and overflow in arithmetic operations. So here, if we consider the example of the implementation of our concept using the MATLAB, then as we know, during the time of the implementation, the MATLAB uses the 15 decimal digits for the purpose of the representation of the coefficients, that is 1 for the sign and 15 for the coefficients here. And for implementation, and if we are using only 15 decimal digits, it means in place of the infinite bits, now we are using only 15 decimal digits for the purpose of the implementation. Naturally, there will be a deviation from the designing concept in this case. And for implementation, need to quantize coefficient to the word length used for the implementation, because if we are using a particular platform or we are using a particular processor, then whatever is the word length decided by that platform or the processor, that will decide the word length of the coefficients or the signals that has to be represented. And due to this type of the representation, here this type of the issues will take place, that is the limitation of the coefficients that will cause the quantization error. As a result, we have there will be the error, so we have to also think about the here the outcome, whether the implemented filter will fail to follow the specifications or that will follow the specifications. So after the quantization, again there is a need of the analysis whether the design filter or the design concept of whatever we have assumed here, it is in the permissible range or outside of the permissible range. So for example, as we have discussed in this case, that is the MATLAB 15 decimal digits will be utilized here. Similarly, in practice, in present day signal processor, this has become less of a problem. For example, with 16 bits are available here. 16 bits means 4 bits for each decimal digit, so 4 decimal digits can be utilized here. Similarly, 24 bits processor, that is the 7 decimal digits are present. In hardware designing, but in the hardware designing, what is happening with the tight speed requirements, this is still a relevant problem here. So during the time of the designing and implementation, we have to use the noise triangle. Here we have to find the triangle of the stability to decide whether the quantized filter or the quantized concept is in the range of the stability or it is outside of the range of the stability. And as we know, the range of the stability is decided by the triangle of the stability here. And for that purpose, here for the second order system, if we use here the second order system, then the second order system will be represented by this transfer function, the second order of the denominator and the second order of the numerator here. And we have to see whether the poles are lying inside the noise here the triangle of the stability, or they are outside of the triangle of the stability. Now, if we see here one example, say with 5 bits per coefficients, suppose what will be the position of the all possible poles, and we have written one program here, and we can see what is the position of the all poles here. Then we will find that low density permissible poles locations takes place at z is equal to 1 and z is equal to -1. Hence, the problems for the narrow band low pass filter and the high pass filter is a serious problem here. We have to focus on these two types of the filters. One is the narrow band low pass and the narrow band high pass filter here. And here the possible remedy is we can follow the coupled realization concept. In this one, we use here the pole zero combination, which we have discussed in the lecture 3, that is the pole zero cancellation concept here. And in this case, the number of the bits, 5 bits will be utilized to avoid the problem. Now, if we see here the coefficient quantization effect on the pole location, then if we consider the example, say the polynomial is given by this one. This is the 1 plus a1 z to power -1 plus a2 z to power -2 plus so on up to the an z to power -n. And roots are the p1, p2 up to the pn. Now the quantized or the polynomial will become 1 plus a1. Here the modified a1. We are saying here the modified a1 because this one is the quantized coefficient here. Similarly, the a2, a3, a4 up to the an, all coefficients will be modified here due to the quantization, in which we are using the finite number of bits in place of the infinite precision here. Now the quantized roots in place of the p1, p2, p3 and up to the pn, now they will be the modified roots, that is the p1 cap, p2 cap, like that up to the pn cap here. So a difference has to be here the analyzed. What is the difference between these two types of the poles? And that will, if we here consider the difference, that can be summarized in the form of the formula like that, in this manner, that is the summation k equal to 1 to n pm to the power n minus k, and n is the order of this filter here, and divided by multiplication of the pm minus pl. L is not equal to the m, and the total one will be multiplied by the difference of the coefficients ak's and ak cap here. Now this is the difference between the two types of the filter. One is the design filter and the second one is the quantized one here. And naturally there is a difference in the positions of the poles and zeros here. So we have to analyze the stability also. And as we have discussed that stability must lie in the stability region, that is the stability of triangle of the stability here. Now the coefficient quantization effect on the zero location. Analog filter design plus bilinear transfer function. First we design the analog filter and then bilinear transfer function takes place for the purpose of the transformation, and this lead to numerator polynomial of the form that is the second order cascade realization, and this can be represented something like in this manner, that is 1 minus 2 cos theta I z to power -1 plus z to power minus 2. Hence, with zeros always on the here, if we see, then we'll find that these zeros will be always on the unit circle. And the quantization of the coefficient is the 2 cos theta I. Its quantization shifts zeros on the unit circle, which mostly has only minor effect on the filter characteristics. Hence, we can ignore this type of the here the quantization error or the effect. Now, if a finite word length effect in arithmetic operation in linear filters have to consider addition and the multiplication. As we know, the any filter equation is represented something like in this manner, that is summation of the a k is multiplied by x n minus k plus summation or subtraction of the b k is multiplied by y n minus k, and in both the cases there will be the limit of the case starting from the 0 or 1. So what is happening? Addition and multiplications are taking place. What will happen in the addition? If two b bit numbers are added, then the result will become the b plus 1 bits here. Similarly, if the multiplication takes place, if b1 bit number is multiplied by the b2 bit number, then the result will become here the b1 plus b2 minus 1 bits here. For example, now two b bit numbers yields a 2b minus 1 bit product here. Typically, and especially in the case of the IIR, where the feedback takes place, the result of an addition multiplication has to be represented again as a b bit because the feedback takes place here. So there is a need to get rid of the either most significant bits or the least significant bits here. So if we are using here the most significant bits, if we are trying to discard the most significant bit, then what will be the here the effect? This is the first option, and in this one, if the result is known to be upper bounded, so that the most significant bits are the bits are always rounded, and they can be dropped here without any loss of the accuracy. This implies we have to monitor potential overflow and introduce scaling strategy here. In the case of the scaling, we have to multiply. There must be some number, and we have to decide that number which will be utilized for the purpose of the multiplication here. In option 2, if we are interested in order to discard the least significant bits, then the rounding or the truncation to the least significant here the total bits introduces the quantization noise, and the effect of the quantization noise is usually analyzed in statistical manner and this causes the limit cycle oscillation due to the non-linear effect. Now the scaling problem, finite word length, if we consider here the finite word length implementation, that implies the maximum representation number here, then what will happen due to this scaling effect? Now the overflow may take place, and digital overflow may lead here the to polarity reversal, or that may cause here the stability also, and that will become the harmful. And to avoid the overflow, we have to use a concept of the scaling, and for the purpose of the scaling, now the transfer function hz will be modified as the c multiplied by the sz. So we have to decide the value of the c here. Now if we see here the time domain representation and say this is the input signal uk, we can write this one is the uk or the xk, and say this is the finite input here. That is the mod of this one is less or equal to the u max, that is a finite value here, and that is the maximum value. Then output signal will be also bounded here, and that will become, that is the mod of the output. This will be the mod of the this here the output equation, that is the convolution sum here, that is the hi multiplied by uk minus I summation of this series from I is equal to 0 to infinite here. This will be less or equal to the hi its mod multiplied by uk minus I, its mod here with the summation series same, and this will be again here the we know this is the shifted input, and the input has the maximum value u max, so this may be written as the u max multiplied by the summation series, that is I is equal to 0 to infinite hi, and here this will become the, this value is written as the sum total summable value of the hz. So here the to satisfy this one, that is the yk is less or equal to the maximum value of the y. Here we have to decide the value of the c, and now this what will value of the c? C will become here the whatever is the maximum value of the output divided by u max divided multiplied by summation total summable value of the h. Now, if we see the example, suppose there is an example given as the Hz is equal to 1 upon 1 minus 0.99 z to power minus 1. Say this is a transfer function of any filter, and this filter may be represented something like in this manner here. Now, if we are interested in order to scale, in order to avoid the overflow, that is the scaling has to be introduced here. And suppose we consider here the input as the 12 bit, that is the output of the 12 bit A to D converter, and we assume that the arithmetic for the output is the 16 bit. So here the maximum value of the output will become the 2 to the power 16, and since the input is the output or input has been taken from the 12 bit A to D converter, so the input's maximum value will become the 2 to the power 12 and the total summable value of the h. And now if we see here the total summable value of the h, then we'll find it is nothing but the total value of this one hi, I from 0 to infinite here, and this will become 100. So if we put these values, then we will get here the c is equal to 0.16, that is 1 upon 2 to the power 3 here. Hence, input uk have to be shifted by the 3 bits to the right side before entering to the filter here. So here the scaled version of the filter will be represented in this manner here. That is the first input will be shifted towards the right side by the 3 bit, and then the filtering or the processing will take place here. Again, we are repeating this one. That is the in this example we have decided what must be the value of the c. And what is the c? This is the scaling factor. Why we are using the scaling factor? To avoid the overflow. So here, if we are interested in order to get the value of the c, then the c will become the maximum value of the output divided by the maximum value of the input multiplied by the summable value of the transfer function here. And for that purpose, we have considered one example. And for that purpose, we have taken the transfer function of the digital filter, that is the first order digital filter 1 upon 1 minus 0.99 z to the power minus 1. And here the total summable value of this one will become the 100. And we have assumed that the input is from the 12 bit A to D converter. So its maximum value will become the 2 to the power 12. Similarly, we have assumed that we are using the 16 bit arithmetic for the yk. So the output's maximum value will become the 2 to the power 16, and hence we can say the c is this has a value of the 2 to the power 16 divided by 2 to the power 12 multiplied by whatever is the summable value, absolute summable value of the h, and this will become the 0.16, and it is 1 upon 2 to the power 3. It is 1 upon 2 to the power 3 means the whatever is the input that will be shifted by the 3 bits to the right side before entering to the processing or the filter processing here. So due to this shifting, what will happen? Naturally, there will be loss of the accuracy. Now, as we have discussed the time domain scaling, similarly we can decide here what will be the value of the frequency domain scaling here, and we can get this value here, that is the c will become the y max upon h max here multiplied by the u, that is the input, its absolute summable value here. The proper choice of the scaling factor in general is a difficult problem, and we have to decide using the different type of the algorithms and concept for the scaling factor here. Now, if we using the L2 norm for the purpose of the decision of the C here, then using that one we can say the C will become the Y max upon this, using this formula here. This will become the under root E max and then multiplied by the summable, absolute summable value of the H. Now, what is happening? Whatever is the value, the input that will be shifted, and then this will be applied to the here the processing concepts that has been represented here the graphically. So we have discussed in this one the scaling concept using the here the this one value of the C, and we have decided how the C will be calculated here. And as we know, if there is a quantization error, then again there is a feedback, and due to this feedback the limit cycle oscillations will take place. Now, for the purpose of the rounding, truncation and magnitude truncation, we can use the different type of the approaches, and these approaches are represented here. In the case of the rounding, the probability error mean it becomes the 0. Similarly, in the case of the truncation, the mean becomes the minus 0.5 LSB, that is the bias here, and in the case of the magnitude truncation, its mean is 0, and the variance that is here the quantization error, we can say this is nothing but this one is the, we can say delta V square by 12 like that, that is 1 upon 12, then LSB its square, and here the 1 by 12 LSB its square, and in the case of the magnitude truncation it will become the 1 by 6 LSB square. Now, statistical analysis based on the following assumptions will take place. One is first is that each quantization error is random, and as we know here, whatever is the total number of bits, that will be truncated to a finite number of the bits. So a random number of the truncation will take place. So what will happen? The quantization error will be also here the random, and the quantization error at the output of a given multiplier will be represented by the uncorrelated or the independent, and that will be represented as the white noise assumption here. Quantization errors at the output of the different multipliers are uncorrelated and the independent, and one noise source is inserted for each multiplier when we are interested in order to develop the model of the any quantized filter, because so far we have discussed the designing concept, and in the during the time of the designing we have to represent the designed filter using a architecture. Now if we are introducing the concept of the quantization, then naturally the quantization error or the quantization noise will take place. So we have to introduce a model that also includes the quantization noise. Since the filter is linear filter, the output noise generated by each number sources is added to the output signal here. So the total error will be assumed at the output here. So as you people have to appear in the interview, so we are concluding this lecture, and in the next lecture we will discuss the modeling of the here the quantized filter in order to analyze the quantization noise. So thank you. Have any question, please?